Hello, everyone, and welcome to this lecture in the Build Large Language Models from Scratch series. Today, we are going to look at a very important topic, and that is regarding loss functions. When you look at machine learning and traditional machine learning models such as regression and classification, the loss function for these type of models are pretty well defined. For regression, you generally use the least square type of a loss, mean square error. For classification, you use cross entropy loss, hinge loss, etc. However, the question is that when we come to large language models, how do we define the loss function? How do we measure whether the large language model is doing a good job or whether it's not performing well? Let's find out in today's lecture. So, up till now in this series, we have covered stage 1 of building a large language model from scratch. In stage 1, we essentially covered three submodules: data preparation and sampling, attention mechanism, and LLM architecture. In each of these subcomponents, we devoted a huge number of lectures and whiteboard notes and also coding, so that by the time you have reached this stage, I hope the building blocks of how to construct a large language models are clear to you. In particular, till the last lecture, we have seen this GPT or the LLM architecture which we have built from scratch. And up till now, we are at a stage where the GPT architecture which we have built and whose code we have written takes an input text and it returns an output. We also saw how this output is converted into the next word prediction task. So our GPT model up till this stage, or our large language model which we have set out to build, is at a level where it takes an input as a text and it can predict next tokens or it can predict next words. That's awesome, right? But now we want to make it better and better and better. In particular, if you remember where we ended the previous lecture on LLM architecture, we got this kind of so we gave the input as hello I am, and the next tokens which we got are something completely random. So now, from this lecture onwards, what we'll be doing is that we'll be looking at stage 2. Stage 2 of building a large language model just centers around one word, and I'm just going to write that one word here, and that is called as training. We need to train our large language model so that the next token which it predicts makes sense. The first step of the training procedure is that you need to ask yourself, okay, let's say my large language model is giving me an output and I know it does not look good. How do I capture this qualitative intuition of knowing that it does not look good into a quantitative metric? And that quantitative metric is generally the loss function. So if we can define a loss function which quantifies how good or how bad our LLM performance is, we can aim to minimize the loss so that the LLM can do better and better and better. And once we construct a loss function, it opens the door for integrating gradient descent based backpropagation algorithms, which we have already learned in neural networks. So then we convert the problem of training a large language model into a problem which we have previously solved before. So, what we are going to do in these set of lectures is we are going to look at this entire pipeline of 7 steps which I have shown over here. In today's lecture, we are going to look at the first 2 steps here. We are going to look at how text is generated, which we have already seen before, but I want to quickly recap it in case some of you have come to this lecture directly. And then we are also going to look at text evaluation, which means we are going to define a loss function in this lecture itself, and we are going to see how that loss function quantifies the loss between what our LLM has generated and the good output which we actually want. In the subsequent lectures, we will be looking at taking an entire data set, feeding it into the LLM, getting the output, and finding the training and the validation losses. We'll then generate the LLM training function, that's the backpropagation I was talking about. And then, towards the end of this series on training LLMs, we'll also load pre trained weights from OpenAI. All that will come next. For now, let's just start with these initial two goals for today's lecture, and that is text generation using LLMs and text evaluation. First, I want to quickly recap how can we use the LLM or the GPT-2 architecture which we have trained so far to generate text. Okay. So the way it works is that we have to specify a GPT configuration. And this GPT configuration or the LLM configuration contains many parameters. First is our vocabulary size. This is the length of the number of tokens we have in our vocabulary. So we are using the same tokenizer which GPT-2 and in fact all OpenAI models used, and that's called as tick token. So this is tick token, and what it does is that it uses a byte pair encoder and it creates a vocabulary of tokens like this. The vocabulary size which GPT-2 had is 50257, and that's the same size which we have when we constructed our large language model. We have to specify a context length. GPT-2 used a context length of 1024, but for the purposes of easy calculation, which you can train on your own local machine in less than 2 to 3 minutes, we are using a context length of 256. Keep in mind that you can just use the same code for a longer context length as well, but just make sure that you have enough compute power and memory to execute the code. Then we have the embedding dimension, which basically means that the token embeddings need to be projected into higher dimensional space to capture the semantic meaning. Then we have the number of attention heads. So these are the number of self attention mechanism blocks we have within one transformer. Why do I say within one transformer? Because there is not one transformer, there are many transformers, and the n layer specifies how many transformer blocks we have. Dropout rate is can be set to 0 also. This is the dropout layer parameter. And query key value bias is basically when we initialize the weight matrices for the query key and value, we don't want the bias term. If any of these terms are looking unfamiliar to you right now, please revise the previous lectures we have had on uh, LLM basics, attention mechanism, and GPT architecture. Awesome. So the GPT model which we built earlier looks something like this. What this model does is that it takes in the input tokens, it converts them into token embeddings, adds positional embeddings to it. Then we have a dropout layer. This output up till layer passes through the transformer block. After we come out of the transformer block, we have a final normalization layer, and then we return the logits. Now these logits which are returned consists of the tokens, and for each token we have the number of tokens equal to vocabulary size. Sorry, for each token we have the number of columns equal to the vocabulary size. I'll come to this part later and I'll explain to you again what we have done in this part of the code so that it's revised for you. Okay, great. Now let's start looking at the first section of today's lecture. Okay, so let's start with the first part of today's lecture. Remember that to get the loss function, we need the input. From the input, we'll get the predicted values, and we should already know the true values, which I'm going to call as target values. In today's lecture, whenever I use the word target, remember that it stands for the true values. And ultimately, the loss function will be determined by the predicted and the target values and how close they are. So in the first section, let's look at the inputs and let's look at the targets, which are the true values. Okay. So the input to the large language model which we are building comes in a format like this. The input is a tensor, and the number of rows here correspond to the number of batches. So I have two batches over here, and that's why there are two rows. So two batches corresponding to the two rows. I'm writing two over here. The first row corresponds to the first batch, the second row corresponds to the second batch. Now you will see that every row has three tokens here, which is usually set by our context size, and I'm just assuming context size equal to 3 for this example. So for the first batch, the input tokens are every, effort, moves. For the second batch, the input tokens are I really like. Now the thing is, based on these inputs, our task is to predict the next word, right? And so for targets, you must be thinking that the target should only be two token IDs. For the first batch, we need a token ID. For the second batch, we need a token ID. But now look at this target tensor over here. It has two rows corresponding to the two batches. That's fine. But why does the first row have three values? And why does the second row have three values? The reason is because whenever you look at the input like this, there are actually three there are actually three prediction tasks which are happening here. When every is the input, effort should be the output. That's why the first target is 3626, which corresponds to effort. When every effort is the input, which means that 16833 and 3626 are input, 6100 is the output, which is moves. And then finally, when every effort moves is an input, the output should be u. So the correct answer which we want is u over here. Similarly, for I really like, there are three prediction tasks. When I is the input, really is the output. When I really is the input, like is the output. And when I really like is the input, chocolate is the output. So we want the output to be chocolate in this case. But then there are three prediction tasks here, and that's why the target tensor consists of two rows. First row corresponds to the first batch, second row corresponds to the second batch, and then we have three values. I hope you have understood why there are three values in the target tensor, because that will be very important to keep in mind as we move forward. Ultimately, we are just concerned about the last word, right, which is this 345. That is the token ID corresponding to you, and 11311. That's the token ID essentially corresponding to chocolate. But the first two are also important for the initial prediction tasks in this input. Okay, so these are the true values which we want. So this tensor are the true values, true prediction values. If our large language model is doing an amazing job for these two inputs, the prediction should be the first tensor of the output should look like this. The second row of the output should look like this. But of course, initially, when the large language model is initialized randomly, it won't produce these outputs which we want. We'll need to train it. Okay, so we have looked at the input and we have looked at the target. Now let's see the outputs, which are the predicted values of our LLM. So this is the input which we saw over here, right? 16833 Then that's the first batch. The second batch is 40, 1107, and 588. So this input will go to our GPT model. And what is the GPT model? The GPT model looks something like this. So the input which I told you goes over here, and then it passes through all of these steps, and then we have an output tensor which is also called as the logits tensor. Okay, so the first step as to what happens in the GPT model is that the tokenizer is converts the tokens into token IDs. Then the token IDs pass through all of these steps and we get the logits tensor. And finally, the logits are converted back into token IDs, which are the next predictions of our large language model. This entire sequence is encoded in this figure here, which I want to explain thoroughly. First, we start with the vocabulary. And for the sake of simplicity, let's assume that the vocabulary just has 7 elements. Remember, in the actual example which we are going to consider, the vocabulary actually has 50257 elements. But I'm just illustrating this diagram for the sake of simplicity, where there are 7 elements in the vocabulary, right? And the input text, let's say, is just one batch for now, and every effort moves. That's the input, right? The first step is to use our vocabulary to map the input text to token IDs. So every is token ID number 2, effort is token ID number 1, and moves is token ID number 4. So first we take these tokens and map them into token IDs 2, 1, and 4. The second step is that we'll pass all of this through the GPT model, and the GPT model will give a logits tensor, and to the logits tensor we apply the softmax distribution, and we'll get this output matrix. Look at this output matrix here. I'll just write its dimensions here. So this output matrix essentially, it has let me use a different color. It has three rows. The first row corresponds to every, the second row corresponds to effort, and the third row corresponds to moves. Now you'll see that the number of columns are equal to 7. 1, 2, 3, 4, 5, 6, and 7. And we have some values. See, every row has some values, and there are 7 columns corresponding to every row. Basically, the values in each row corresponds to the probability of what the next token will be. So let's look at the first row values, and I'll just write them over here for your reference. 0.1, 0.6, 0.2, 0.05, 0, 0.02, and 0.01. These are the values corresponding to every. Now, what these values means is that when every is the input, what is the probability for the next token being the output? And 1, 2, 3, 4, 5, 6, 7 corresponds to a effort every forward moves you and zoo. So let me write the effort every forward moves you and zoo. This is the vocabulary, right? Now, every value here in this row corresponds to the probability of what the next token will be if every is an input. So let's analyze this probability. If every is an input, the probability that the next token is a is just 10% or zero point 0.1. There is 60% chance of the next token being effort, 20% chance of the next token being every, etc. So then what we do is that we look at the index with the highest probability, which is this zero point 0.6 over here, and so we know that the next token is equal to effort. Now when every effort is the input, we again look at the second row. So we again look at the second row and find the index which has the highest probability, and that corresponds to moves. So this is index number 4, and that corresponds to moves over here. Then we look at the third row. So every effort moves. When that's the input, what's the output? And this is the main prediction task because it actually predicts the next token. And if you look at the third row, you look at the index which has the maximum probability, and that's index number 5, which is here. And we know that index number 5 corresponds to u. So we know that the next token is u. So remember when I told you that when the input has three tokens like this, there are three prediction tasks. For the first prediction task, the output is index number 1 because that corresponds to the highest probability, and the token which it corresponds to is effort. For index number 2, or sorry, for the prediction task number 2, the input is every effort and the output is index 4, which corresponds to moves. And for the third prediction task, the input is every effort moves and the output is 5, which corresponds to u. So when you give this input, every effort moves, to the uh, large language model, the output is a sequence of indexes 1, 4, and 5. What this output means is that 1, so if you look at 1 over here, it means that when every is an input, effort is the output. When every effort is the input, moves is the output. And when every effort moves is the input, u is the output. So this is what is actually happening within the GPT model itself. I just gave you a 5-minute crash course of what we learned in 4 to 5 hours in the previous set of videos. So if any of this you're finding hard, I would again highly encourage you to go through all the previous videos so that you understand this better. For now, even if you get an intuition of what's going on here, it's fine, and you can follow along till the next part, right? So here what I want to illustrate to you is that this process which I've shown here, we have the input. When it goes to a GPT model, we have the output token IDs, and I've told you how we get the output token IDs. So if you have understood the process, let's say these are the output token IDs which we have obtained. Remember, for actually GPT-2, the vocabulary size is 50257, right? So the range of the output token IDs is 0 to 50257. Here the vocabulary size was 7, so the range was 0 to 7. So if you look at batch number 1, the output tokens are 16657, 339, and 42826. And let's look at the inputs, right? Every effort moves. So every effort and moves. What this output essentially conveys is that if every is an input, the token corresponding to the token ID of 16657 is the output. When every effort is the input, the token corresponding to token ID 339 is the output. And when every effort moves is the input, the token corresponding to the token ID 42826 is the output. And what do we want these token IDs to be? We want these token IDs to be as close to the target token IDs which we saw. Look at these target token IDs. The token IDs which we have obtained right now are not the actual token IDs because the training has not yet happened. So these are the output token IDs, and we want these output token IDs to be as close to the target token IDs as possible. That's the whole goal of today's lecture. And so we are going to then define the loss function between the outputs and the targets. So these are the output token IDs for batch number 1, and here you can see that these are the three output token IDs for batch number 2. where the input is I really like. So I really like. And for these outputs, we have to compare these outputs to these true values for the second batch. I hope you have understood the goal of today's lecture. Uh, Up till now, we have understood what are the inputs, the shape in which inputs will be given to the model, what are the true values, which I am also calling as targets, and we understood that what are the uh, output token IDs for batch number one and batch number two. And to get these output token IDs, the inputs have to go through a huge transformer block, and it has to go through this whole GPT architecture. Then we get the output logits, we apply softmax, and we get this tensor like this. This one tensor essentially contains all the information. You take a look at this tensor and then you extract the indexes with the highest probability in each row. That is essentially your output. Okay. And now what we are going to do next is that we are going to then find the loss between the targets and the output. Before coming to the next step, I want to go to code and really code everything what we have learned so far, so that the understanding is clear, and so that you also understand what is really going on in the code. I already explained to you the configuration which we are going to be using, right? Vocabulary size 50257, the context length of 256, embedding dimension of 768, number of attention heads 12, number of transformer blocks equal to 12, dropout rate zero point 0.1, and the query key value bias equal to false. Awesome. Now, the next thing what we are going to do is that we are going to construct our model. What this model is basically, it's an instance of the GPT model class. And this is the GPT model class which we have defined previously. To get a visual representation of what this class does is that it takes in the input and then it converts the inputs into this logit tensor. That's so all of these steps which have been written here are actually encoded visually in this transformer block or in this GPT model architecture which I've seen. The blue color which I'm highlighting right now with the orange pen, that's the transformer block, and it's the heart of the entire GPT architecture. So here we are creating an instance of this model so that when we pass an input to this model, we get the logit tensor as the output. One note is that we reduce the context length of only 256 tokens here. Although we know that the GPT-2 model uses 1024 tokens, the reason is because you all will be able to follow and execute the code on your laptop computer, and we reduce the computational resource requirements that way. Okay. There are two more functions which I want to define. The first is text to token IDs. What this will do is that whenever we get any text, which is the input, we'll just convert it into token IDs, and this uses this tick token tokenizer to convert the text into token IDs. And there is also token IDs to text, which is the reverse function. So basically, when we get any token ID, we'll convert it back into text. So if every effort moves you is the text, and when you pass it through the tokenizer, you will get the token IDs corresponding to this, and then you can even decode the token IDs, and it will get you back the same text. Just as a proof that our model is working, what I've done over here is that I have used this generate text simple, which is another function we have defined in the previous lecture. No need to worry about this right now. But what this function does is that it takes in our model and we predict the maximum number of new tokens. The number of input tokens is 4, every effort moves you, and then it generates 10 new tokens. So here you can see we have printed the output text, and this shows that the output text consists of 4 input tokens and 10 output tokens. Remember, one word is not necessarily equal to one token because we are using the byte pair encoder, where we even have subwords and characters which can be individual tokens. So up till now, as we see, the model does not produce good text because it has not been trained yet. And so what we'll be doing is that how to measure what good text is. So that's why we have to define the loss function, right? Now let's start with the main implementation in today's lecture, and these are the inputs. So the first input, as I told you on the whiteboard, is every effort moves. These are the token IDs corresponding to the input text, and the second input is I really like, and the token IDs which are corresponding to the second input text are 40, 1107, and 588. Great. and the targets are essentially 3626, 6100, 345. These are the true values for the first batch. For the second batch, the targets are 1107, 588, and 11311. Take a note that the targets are the inputs shifted by one. So if you take the inputs and shift it, or just take the last two values here and add a new value, that's the targets. This is because there are three input output pairs. Okay, now once we get the inputs, what we are going to do is that we have the inputs and we have the targets, but we have not yet generated the outputs. To generate the outputs, what we'll do now is that we'll pass in the input through this GPT model. We'll pass the input through this GPT model block and generate the output token IDs in this kind of a format which I've shown you. Okay, so the first step is that remember that when you pass the input through the GPT block, it returns these logits, and which are not converted into a normalized 0 to 1 format. We have not applied softmax. So the first step is that to get these logits and pass them through a softmax. Always keep an eye out for dimensions. Why is it 2 comma 3 comma 50257? The reason is because everything can be explained through this diagram. Look, when the vocabularies, so let me first rub many things here just so that things become a bit easier to understand. Okay, so look, when the vocabulary size was equal to 7 over here, take a look at the form of this logits tensor. So if the vocabulary size was equal to 7, for one batch, the logits tensor size was 3 rows and 7 columns, right? Now if there are two batches, the size would have been 2, comma 3, comma 7. That's the general size of this logits tensor. So it's batch size. The second is the number of tokens, and the third is the vocabulary dimension. So in this case, the vocabulary dimension was 7. So there are 7 columns. In our case, there are 50257 columns. So this third dimension will be 50257. So here we see that the logits tensor is converted into a tensor of probabilities whose shape is batch size, number of tokens, and vocabulary size. So that will be 2, comma 3, comma 50257. Great. And now what we'll do, as I mentioned to you, the next step is that we extract from each row the index which has the maximum value, and that will be done using the argmax function. And these indexes with the maximum value, that's our output from each given batch. So what we are now going to do is that we are going to do torch.argmax. You can even go to the PyTorch documentation and see what argmax does. Argmax basically returns the indices of the maximum value. So we are doing torch.argmax dimension equal to -1, which is along the column. So what this will do is that it will look at all the values in the columns and give the index of the value which has the give the index which has the maximum value. And so here we see for the first batch, there are this is the first tokens output, second tokens output, third tokens output index. Remember, these are token IDs. For the second batch, this is the first tokens token ID output, this is the second output token ID, this is the third output token ID. And these output token IDs are the ones which we want as close as possible to these target token IDs. That's the main goal. And for this, we are going to construct a loss function. So now actually let's decode these tokens. Remember, we have already written a function which decodes here we have written a function which converts token IDs into text, right? Let's decode these tokens in the output and let's see what they mean. So we have passed our input into a GPT model and we have got these outputs, and let's decode these now. So if you decode for the first batch, the input is effort moves you, and the output is armed he Netflix, completely random output which does not make sense. We want this output to be uh, every effort moves you, yeah. So input, so the target is every effort moves you, correct. This is the true value. So we want the target to be effort moves you, but the actual output which we have got is armed he Netflix. So if you look at the first batch, you can see that there is a huge difference between the targets and the outputs, right? Which makes sense because, well, we have not yet optimized. We have not even defined the loss function. We have not tried to minimize the loss function. So ideally now what we'll do is that we'll define a loss function between the targets and the outputs from both the batches, so that the target output and the so that the target text and the output text will be as close as possible to each other. Great. Now that actually motivates us to go to our next section in today's lecture, which is actually defining the loss between the targets and the output. So now let's see what's going on here. So we have the inputs, and this is the probability tensor, which indicates what's the probability of the next token for every input token. What I've marked in blue over here is the target indices. So if we want the actual answer to be that for every it should be effort, for every effort it should be moves, and for every effort moves it should be u. The the correct answer of the indices which we want is 1, 4, and 5. These are the true values. So the token IDs here are 3626, 6100, and 345. But in the sample code which I've shown over here, we just has seven vocabulary size. The token IDs which are 1, 4, and 5. Those are the correct ones. So now one thing which I would like to mention is that let's say these indexes which are marked with the star right now, these are the actual indexes which we want, right? But if you see the values corresponding to those values are not the highest because our LLM is not trained yet. So what I'm going to do now is that I'm going to collect the probabilities at these indices. So I'm going to take this index, I'm going to take this index, and I'm going to take this index, and I'm going to find the probabilities at these indexes, or these indices rather, and I'm going to collect these together. So for example, for the first batch, what I collect can be 0.14, 0.14, and 0.13. These are the set of probabilities. And for the second batch, I'll collect another set of three probabilities like this. This is exactly what we are doing in the actual problem. In the actual problem, we know that the target indices are these. So what I'll do is that I'll look at my probabilities tensor, and I'll get the probability which is corresponding to these indices. I know it will not be maximum because my LLM is not optimized, but I'll just write down these probabilities for now. So I have these target indices, and let me call them I11, I12, I13 for the first batch, and I21, I22, and I23 for the second batch. So what I'll be doing now is that I'll be looking at batch 1, and I'll be looking at batch 2, and I'll find the value corresponding to these indices in the probabilities tensor. So in the probability tensor, which will look something like this for the 50257 vocabulary size also, I'll find the probabilities corresponding to I11, I12, and I13 for batch number 1, and I'll find the probabilities corresponding to I21, I22, and I23 for batch number 2. So for batch number 1, I'll aggregate these probabilities together, and they look like this: P11, P12, P13. For batch 2, I'll aggregate these probabilities, and they look like P21, P22, and P23. Remember, these are the probabilities which are not maximum right now. The goal of our training is that to get all of these values as close to 1 as possible. And why do we want all these values close to 1 as possible? Because then we'll make sure that the output indexes which have the maximum probabilities will be closer to I11, I12, I13, I21, I22, and I23, which are my targets. So the goal of the LLM performing better now is reduced to this problem, that I want these probabilities to be as close to 1 as possible. I want all these six probabilities to be as close to 1. Why are there six probabilities? Because there are two batches. Each batch has three tokens. So there are three prediction tasks. So that's why there are three probabilities for the first batch, three probabilities for the second batch. So let me merge these probabilities together, and then this will be P11, P12, P13, and this will be P21, P22, and P23. Now what I want is I want all of these P11, P12, P13, P21, P22, and P23. I want all of these to be as close to 1 as possible. How do I enforce this mathematically? First, let's see the workflow. So we had the logits tensor, we converted it into probabilities through softmax, and then we had the target probabilities tensor. What this target probabilities means is that we have the indices corresponding to the target values So we have these indices I11, I12, I13, I21, I22, I23. These target probabilities are just the merge target probabilities, which is P11, P12, dot 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 up to P23. These are the six probabilities, and we want all of these to be as close to one as possible. To all of you students who have studied classification and the loss, this problem would be familiar. Since we are dealing with probabilities, it's natural that logarithms and cross entropy will come into the picture. So instead of directly dealing with these numbers, it's much better mathematically and from an optimization perspective to just take the logarithm of these values, and it comes out to be this. And then we take the average of all of these logarithm values, and it comes out to be this. And then we take the negative of this average. So that's 10.772. So this is the cross entropy loss. And this is the loss which we want to minimize as much as possible. So to explain this in another way, let's say we have taken this target probabilities, and we find the mean of, so we take the log of this. So we take log p11, log p12, and the last is log p23. And then what we do is that we find the mean of this mean. And so then that will be sigma, which will be the summation of log 11, summation of log p11 dot log p23 divided by 6. And then I'll just take the negative of this, and that's called the negative log likelihood. So then that will be negative of summation of log of p11 dot 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 up till log of p23 divided by 6. So now see, we want p11 to be close to 1. We want p all the probabilities to be close to 1. So we essentially want this negative log likelihood to be as less as possible. So this cross entropy loss we want to be as low as possible and as close to 0 as possible. So why are we taking the negative log likelihood? The reason we take the negative log likelihood is because it just makes more sense. If you don't take the negative value, then the loss function would look reverse of this. The loss function would look reverse of this, and then we'll have to reframe the problem as trying to maximize the loss. Instead, it just makes more intuitive sense if the negative looks like this, and now the whole goal. Instead, it makes more physical and intuitive sense if the log likelihood looks like this. And now our whole goal is to bring down this loss as low as possible. What will happen if this loss is brought down to, let's say, 0? If the loss is brought down to 0, which means that the mean, which means this value is close to 1, which means that there is a higher chance that p11, p12, p13 up to p23 are equal to 1. That is exactly what we want. The goal of training is to get these values as close to 1 as possible. So that is the main hope now. So initially, let's say when we start the training procedure, our value, the x value whose log we are going to take, that will not be close to 1. It will be somewhere, maybe here it will be somewhere 0 to 1, and somewhere here. The goal is to go here slowly, so that the mean of the probabilities will be equal to 1. Okay, so this is the negative log likelihood, and it's also called as the cross entropy loss. And we want to minimize this cross entropy loss as much as possible. That will ensure that the indices at which our tokens, indices at which we predict the next token, that matches with the target indices. So then the output and the target indices will match closely to each other, and then we know that the large language model is actually doing a very good job. So this is exactly what we are going to do right now in the code. One thing which I would like to mention about the cross entropy loss is that the cross entropy loss essentially measures the difference between two probability distributions. So here what we are actually doing is that we are just adding discrete probabilities, but in a sense this can also be called as the categorical, or I should call it the cross entropy loss. So now let's see the sequence of steps which we are going to implement. The Logits tensor, which is a tensor of probabilities, has the shape of 2 into 3 by 50257. Why? Because it looks something like this. So every effort moves, and then we have 50257. uh, so this is the first batch and this is the second batch. What we are going to do is that we are going to flatten this so that these two, first batch and second batch, are merged together, right? So this is my output tensor right now. Every effort moves you, I really like. It's a merging of these two batches. And my target, so my target is 2 by 3. Why is it 2 by 3? Because for the first batch, this is the target index of the first input. Every This is the target index of every effort, and this is the target index of every effort moves. 107 is the target index of I, so it will be really. 588 is the target index of I really, and 11311 is the target index of I really like. So then chocolate. Then what we are going to do is we are going to flatten this out. So then this will be 3626, 6100, 345, 107, 588, and 11311. Now, ideally, what we need is that we are going to look at every year and we are going to look at the index corresponding to 3626. So, let's say if this is the index corresponding to 3626, this will be P11. For effort, we are going to look at the index corresponding to 6100. Let's say it's this one, so that will be P12. Similarly, for like, which is the last, we are going to look at the index corresponding to 11311. So, let's say this is this. So, this is P23. So what we'll get is that we'll get P11, P12, P13, P21, P22, P23. We'll take the log of them, we'll add, take the mean, and then do the negative. This whole process is encapsulated in this just one line of code, torch.nn.functional, cross entropy, logits. So this is the logits flat. I'm calling this logit flat tensor. And the second argument here is the targets flat. What this code will do is that torch.nl.function cross entropy, logits flat comma targets flat. First it will convert this logits tensor into a tensor of probabilities. Until now the logits is not does not represent probabilities. So this function will apply softmax to the logits, and then what it will do is that, as I told you before, it will find the negative log likelihood. So first it will find the probabilities P11, P12, P13, P21, P22, and P23 in this logits flat tensor corresponding to the indices in the targets flat tensor. It will take the negative log and then it will find the mean. This one line of code is going to do all of these steps for us. That's why Python is so powerful. In one line of code, we'll not only convert this logits into uh, a tensor of probabilities through softmax, but we will also get the negative log likelihood, and that's the final loss function which we are looking for. So this one line of code is going to give us the loss between the output and the target, and that's why it's a very important piece of code. To do all of these steps in just one line of code, I think it's pretty amazing. But what I want you all to focus on is what we really are doing over here. What we are essentially doing is that we have inputs, and those inputs are every effort moves and I really like. We are passing them through the GPT architecture, and then we get this logits. We get this logits tensor. What we are going to do with this logits tensor is that we will first merge this tensor, merge the batches, and call it logits flat. Then what we'll do is that, corresponding to every token, we are going to look at the indexes which corresponds to the target, and then we are going to find the probabilities. Now in an ideal world, these probabilities will be close to 1, because that would mean that the output and the targets will match. But since the LLM is not optimized, these probabilities which correspond to the target tensor indices will be probably be very small, and our goal is to bring all of these probabilities close to 1 as possible. So that's why we'll take the negative log of these probabilities and take the mean. That's the cross entropy loss. And through one line of code, cross entropy, torch.nn.functional.cross entropy, between these two tensors, we are going to implement this exact same operation which I just described in words right now. So you can even check this, and let me type it: torch.nn.functional cross entropy, and you can check. It finds the cross entropy loss between the input logits and the target. This is exactly what we did right now. Okay, now I'm going to implement this same thing in code. We are going to find the cross entropy loss in code. Okay, so first what we are going to do is that we are going to find the P1, P2, P3. So we are going to find P11, P12, P13, and P21, P22, and P23. That's the first step. So remember here in the sequence of steps over here, first we find these target probabilities, right? And to find these target probabilities, what we'll do is that we'll take the target indices, which are the indices corresponding to the true values. And what we are going to do is that we are going to take the probas. So let me see what the probas is. So this probas is the output. This probas is the output probabilities tensor. And what we are going to do is that we are going to find the token probabilities corresponding to the target indices. And to do that, what we are going to do is that we are going to use this line of code. And what this will just do is that it will take the target indices and it will index, or it will look at this probas, which is the tensor of output probabilities, and then it will look for those particular indices. So basically what it will be doing is that for 0, that's P11, that will be this. For 1, that will be P12, and for 2, that will be P13. Similarly, when we look at the second batch over here, what we are doing over here is that that this is 1, which means that it's going to look at the second batch. So one way to understand what's going on here is to look at the probas and try to see the dimensions. So let me write it here again for reference, just so that your understanding is clear. So the probas is actually, it will look something like this. First, let me write it for the first every effort moves, right? And then this is 50257, the number of columns. And then second is I really like. And the size of this, so this whole thing is the probas tensor, which is the probability tensor, and the size of this is, so we have two batches, we have three tokens and 50257. So what we are essentially doing here is that uh, let me scroll down below. Yeah, what we are doing here is that in this line, text idx is equal to 0, which means that we are first looking at the first batch. So we are looking at this batch, and then what we are doing is that we are looking at row 0, row 1, and row 2. And from row 0 we'll get the, so let's look at the target tensor. We'll get the index corresponding, we'll get the value corresponding to 3626 index. From row 1 we'll get the value corresponding to 6100, and from row 2 we'll get the value corresponding to 345. Now, similarly, here what we are doing here is that we are looking at, so text idx equal to 1, which means we are looking at the second batch. We are looking at the second batch, and then row 0, row 1, and row 2. So then we'll look at the targets tensor again. And for row 0, we'll take the value corresponding to index 1107. For row 1, we'll take the value corresponding to index 588. And for row 2, we'll take the value corresponding to index 11311. So that is essentially P21, P22, and P23. So these three values are the P11, P12, P2, P13, and these three values are P21, P22, and P23. The whole goal is to get these values as close to 1 as possible, right? Then what we'll do in the second step, as I told you over here, once we get these P11, P12, P13, P21, P22, P23, we are going to merge these together, right? So that's what's written here. We are going to concatenate these six values together, and you can see that they appear like this. The next step is that we are going to take the log. Actually, after concatenation, yeah, we take the log over here, and then we print these log values. Then we'll take the mean of these log values, and then we are going to do the negative of the log likelihood. So as I told you, we can also not do the log likelihood and just do positive log likelihood. But then that would mean maximizing the loss. That does not make sense. So in deep learning, it's conventional to use negative log likelihood so that we minimize the loss, right? So this is now the negative log likelihood loss value, which we ultimately need to minimize. Now, as I told you, there is a much simpler way of doing this using the torch.nn.functional cross entropy. The first step of this is to flatten the logits and the targets and to use this one line of code. So that's what I am going to do now. I am going to take the logits, which was earlier 2, 3, 50257, and I'm going to flatten it. I'm going to flatten these first two dimensions together so that it's 6, 50257. This is exactly what we saw over here. Look at this, it's 6, 50257. Batch 1 and batch 2 are merged together. Then what I'm going to do is that I'm going to look at the targets tensor and I'm going to flatten it. So if the targets tensor is this, two rows and three columns, I'm going to merge these two rows into six values. And then I'm going to just write one line of code. This one line of code will first convert these logits into a softmax, and then it will find the values corresponding to the target indices. Then it will take the log of these, the mean, and then the negative log likelihood. All of this will be done, and I will get my categorical cross entropy loss of 10. Remember, I want to take this loss as close to zero as possible. That's the goal. So when we train the large language models later, the goal is to bring this categorical cross entropy loss to as low as possible. Before we end the lecture, I want to show you one last thing. There is another measure of loss, and that's like cross entropy itself, but a minor modification, and that's called as perplexity. So perplexity actually measures how well the probability distribution predicted by the model matches the actual distribution of words in the dataset. And so in that sense, it is more interpretable. And it's more interpretable way of understanding model uncertainty in predicting the next token. And I'll show you why in a minute. Remember that lower perplexity score also means better predictions. So the formula for perplexity is just you find the exponent of the loss. And surprisingly, this simple modification leads to a lot more intuition. So if the exponent of the loss in our case is 48725, it means that the model is roughly as uncertain as if it had to choose the next token randomly from about 48725 tokens in the vocabulary. So the number of tokens in the vocabulary is 50257, I think. Now what this means is that if the input is every effort moves, right? Every effort moves is the input. Currently our LLM is at a stage that to predict the next token, that's as as if we have to choose between 48725 tokens. That's pretty bad, right? It means that there is a lot of uncertainty in predicting the next token. If the perplexity score was equal to 2, that's pretty good, which means that we just need to predict between two tokens. So that means our LLM is very accurate. But in this case, the perplexity score is 48725, which means that 48,000 tokens are kind of equally likely to become the next token, which means that our model is not good at all. You can see how it is more interpretable than getting a categorical cross entropy loss of equal to 10. When I get a categorical cross entropy loss of 10, I don't really know how it relates to my vocabulary size also. But if you get a entropy or a perplexity score of 48725, you can kind of relate it to your vocabulary size and make interpretable predictions like these, that the 48,000 tokens in our vocabulary of 50,000 are equally likely to be the next token, and that's pretty bad because our LLM is not yet trained. So this brings us to the end of today's lecture, where basically what we did is we first started with the inputs, then we started with the true values, which were known as the targets, and then what we did was we found the output values. This was kind of a revision. We got the logits tensor, we converted it into a tensor of probabilities, and then we got these output tokens. So then we tried to find the loss between the targets and the output using the cross entropy loss. And we ultimately saw that using one single line of code, torch.nn.functional.cross entropy, we can find the loss between the logits tensor and the targets tensor. As the lecture concluded, we even looked at another way of measuring loss, which was called as perplexity, which is much more intuitive. And the way perplexity is calculated, it's just e raised to loss, which is exponent of loss. And I've also mentioned the perplexity concept over here. In our case, the loss was 10.79 and the perplexity value was 48725. and this is usually more interpretable. Awesome. In the next lecture, what we are going to do is that we are going to take an actual data set from a book which is called The Verdict. And first, we'll tokenize this data set. We'll divide it into input output pairs, and then we are going to get the LLM output, and we are going to find the loss function or the loss value for this entire data set. Until now, in this lecture, we just looked at in the code we just looked at two sample inputs, right? We looked at we looked at these two inputs. In the next lecture we'll be scaling this up and look at an entire text data set. So next lecture will be a lot of fun, and we'll run the entire architecture on this hands-on example. You can replace this example with any book which you like, Harry Potter book, any other book. So next lecture is going to be a lot of fun. I hope you all are liking these lectures. We have now started a new module which is on the training large language model, and we are slowly making a lot of progress on in building the large language models. We have already finished stage 1. Now we are on stage 2 and rapidly moving towards completion. Thanks a lot everyone, and I look forward to seeing you in the next lecture.